Surely you want this problem on the test. I mean,
Yeah, that's great.
yes, you are allowed to use the, you do not have to derive this on the test. I don't want to grade that. No. I don't get paid enough to grade this. No, 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 no. No. I mean, if we had a physics major, then yes. It'd be on every test. Anyway. I tried to do this three-dimensionally. So basically just go through the same steps but with dot products. And there's just like this one place, everything goes until you get this one place, like you got like this dot product and that dot product. So, I mean, it's the same. See this? It's like, where is it? VB1 minus VB2, VB2 minus VB1. It's like, so it's almost the same, right? So you like, if you could cancel that and get to here, then you'd have the same song and dance. But the thing is, you can't cancel dot products. And in fact, this theorem is no longer true in 3 dimensions. This is a 2-dimensional thing. Excuse me, 1-dimensional thing. Before you accuse me of not doing any numbers today, let's look back at this example. 2 students on spring break in Canada. Maybe imagine a young Ted Cruz and a young Rubio sitting on a nice pond in lawn chairs. Of course, why not? One of them has an umbrella, and a strong wind sends student A on a collision course with student B. Okay. Supposing the mass, wow, skinny. Mass A is 5 kilograms, and he has a velocity of 2 meters per second after the wind sets A in motion. If mass of B is 3 kilograms, initially at rest, and after the collision, the velocity of A2 is 1 meters per second at 30 degrees, what's VB2? It's a collision problem. There's the ice, there's no friction. It's all horizontal, so gravity doesn't change momentum, unlike our projectile motion problem last time. So this is just raw, unbridled momentum conservation. The momentum before is equal to the momentum after. But this is a genuine 2-dimensional problem. You have to think of momentum as a vector, otherwise you'll be wrong. So the initial momentum is what? It's just like ma times va1. So the initial momentum is totally horizontal. The final momentum then must also be totally horizontal. That means whatever vertical momentum this has, that must have equal and opposite vertical momentum, right? And the net horizontal momentum of both of them together must be matching this. So then we have to do math to figure the details out, but you can see these things conceptually without doing any calculations. So here it is. VA2, I told you that's 30 degrees, so cosine 30 VA2, sine 30 VA2. This 1 meter per second was given, so I can actually plug numbers in there. VB2, I don't know. There's some angle beta, I don't know, but I know that cosine beta BB2 minus sine beta VB2 should give me a breakdown of this velocity into its horizontal and vertical component. A lot of times in a problem like this, it's important to make up names for the things you don't know. If you try to solve it all without writing down some kind of intermediate step, you usually can't do it, right? Just something to think about as you're trying to solve problems. So momentum conservation then, in the x direction, ma va1 is equal to the sum of the x momentums of A and B, right? This I don't know. Okay, I deal with it, I write it down. And y, 0, is the x momentum for A plus the y momentum for A and the y momentum for B. It's obviously negative. This is obviously positive, right? And then you gotta do algebra. So you solve for, what do I want? I want VB, the x component of VB2, which is this. I can solve, let's see, how am I getting this? Oh, everything here I know, right? I know this, I know this. I know this. I just don't know cosine beta times v2, right?
Professor,
Yep.
what is this a one-dimensional problem? Why are there cosines and
This is a two-dimensional problem. I shifted gears.
stuff? This is not the state umbrella ice launcher problem? maybe?
That is the same problem, but it's on a lake. They hit and they go off at an angle.
Oh, okay.
Yeah. Okay. So it's cool. So I think the first one, everything I know, everything here is given except for this term, right? So I can solve for that. I can solve for cosine beta times v2. I get 1.89 meters per second. VB2y, where's that? That's this thing. I can solve for that also, and I get that. So I know that VB2 is equal to this, and then I can use trigonometry to figure out what the angle and magnitude is and such. So I get minus 24 degrees for beta, and sum of the squares, square root of the sum of the squares gives me 2.1 meters per second. I've asked a question like this on many tests. I usually ask some question like this because I want to see, can you add vectors? Do you understand that momentum conservation, generally speaking, is a vector? It's a vector equation, right? You have to think in terms of vectors. That said, there are lots of non-trivial, interesting one-dimensional questions that you don't need vectors for, right? And there's always the question, here's two masses, right? They come together, they collide, and here's their velocities afterwards. Is this possible? Right? Is this possible is one question I can ask. Is it elastic is another question I can ask, right? Is it possible? What do you have to check there? There are a couple things. Yeah, momentum must be conserved. That's the big one. Short of an explosion, there really shouldn't be more kinetic energy before and after versus after, right? So that's kind of a. So you should have really a loss of kinetic energy in a collision, right? You shouldn't, as a system, you shouldn't have a collision and then come out of it with more energy, right? I mean, you might be able to sell that to people in terms of some like peer-to-peer multi-level marketing scheme, but short of that, I mean, in the world of actual logical constructions, things that are real, not things that are based on taking advantage of weak-minded people, we should have less energy after the collision, I think. Sorry, pet peeve. All right, so I guess I'll pick up this problem next time, but only after I've answered your homework questions, okay? Thanks, guys.